any sort of session management or anything like that. Okay, so it just simply becomes a router connecting a wireless network to a wired network. Okay, so this is more like an idealistic scenario, but with the growth of technology, this could be feasible, or this is probably feasible already, okay, with all these advanced devices. So these two are kind of solutions proposed by the WAP 2.0 protocol suite. And the main difference between the previous version of WAP and this is the previous version requires you to run the wireless versions of all these TCP/IP protocol stack protocols, like all the ones that we saw, WPS, WDP, and all those things. But here, with the 2.0 version, you basically run the TCP/IP protocol stack on this mobile terminals. Okay? And this is a more common solution or feasible solution where you have to run two TCP sessions, one between the device and the gateway, and then one from the gateway and the wired device. Why? Because you still have wireless network, so it has its own characteristics, packet drops, limited bandwidth, and all those things, whereas you have more bandwidth and few packet drops and all those things in a wired network. So that's why you have to have separate TCP sessions. But as the wireless networks become more sophisticated, the bandwidth grows, and the terminals also have more buffering capacity and all these things, then you can even run a single TCP session between the mobile terminal and the web server and provide all your encryption, incorporate all your encryption at the network layer with the IPsec standard. Okay? So that way you can provide what is called end-to-end security from the mobile terminal all the way to the wired server. Any question? Alright, so with this we actually complete this chapter, and as well as we want to start this biometrics. Have anybody studied biometrics before?
We did a little bit in your networking course last. Yeah.
Biometrics is basically more like a form of authentication that you cannot easily forge, fake. Like for example, we have this ID cards, but it's not really indicating unless there is someone to verify that you are the one holding ID card. Like anyone I give can open the door, right? If I give my ID card to any one of you, you can open the door, right? If it's more automated or kind of authentication, there's no verification, right? Whereas biometrics, you cannot fake the biometric signatures. So for example, if you use a fingerprint, right? You don't have two people having the same kind of fingerprint, right? Similarly, the iris image of your eye, retinal scans, and all those things. But there are some biometric signatures which are kind of overlapping. So, for example, if you use voice recognition as your biometric signature, someone can speak like some other person, right? So that's not a unique way of identifying people, right? So that's in that context, there are two broad categories of applications of biometrics. One is to just verify that you are the particular user. Okay, so that's kind of secondary means of authentication. So always when you do authentication, authentication means what? You're trying to make sure that this is the right user who's trying to do something. You're trying to have what's called multi-factor authentication. So which means you're trying to have more than one way of authenticating a user, and the user has to pass all these tests. So for example, you could ask the user to first enter a password, and then you check whether the password is really what the user is supposed to enter, and then you could ask him to go to some biometric identification. But that is again secondary form of authentication. So there you can use even the weaker biometric kind of identifiers, for example, your voice or something that he can forge, but he cannot also, there's likely someone can forge the password as well as the voice, right? So the combination has to really, like multi-factor means he has to pass in all these tests, okay? But if you want more kind of unique way of authenticating people, then you really go for the more sophisticated biometric antivirus like the iris image. You know what an iris means, right? It's part of an eye, or a retinal scan, or a fingerprint, and all these things. They are more guaranteed to be unique for each person. Okay? So that's again a very high level overview. So of course when you collect the biometric samples, like how you verify whether this is a user who owns this biometric sample, you have to collect a lot of samples, right? So you have to kind of populate the database. Even when you, say for example, voice recognition or even signature recognition, all this kind of biometric systems, you cannot sign exactly the same way as you sign once, right? So when you go to banks and all, they collect some sample signatures, and they ask you to always sign more than once, like 3 or 4 samples, right? So why? Because if you automate all these things, then when you really want to get authenticated, the way you sign may not exactly match with one sample in the database, but if it matches with any one of those samples in the database, then you can be let in, right? So biometrics could have some false positives and false negatives, right? Mostly false positives. Why? Because the samples may not be accurate enough to capture all your different variations, right? Similarly, voice recognition, you might have experienced all this customer service that when you call over phone and they ask you to tell something and they don't understand what you tell, right? So that's a kind of voice recognition. That's again because they are not properly designed to sample all your voice signals and kind of extract what you're trying to say. So if your voice recognition system software is kind of weak and it cannot really sample all your voice signals, then it cannot be able to recognize you. If you have a sore throat or something and voice recognition is the primary means of authentication, then you cannot really log into the network or computer, right? So it has its own weaknesses. So you have to collect a lot of samples, populate the database, and then do a lot of testing. Okay, so it's not like a password-based authentication or an ID card-based authentication. Just collect one sample or just store one password you can log in. So you have to collect a lot of samples of the user. Okay? So that's all. That's kind of very high-level overview about biometrics. So you won't be tested on it, but at least you got to know something about it, right? Okay, so I have posted question bank for a final. So mostly on network security, but there are other chapters too. Especially the chapter on programming. Since I didn't see many submissions yet, and still need some way to test you, right, whether you understood that. So I have posted some questions on this chapter for you to go through. Okay. So you may be required to write a small piece of code, or go through a piece of code and write what is the output, or why you will get some output when you are telling, okay, this is the output, so but then you should be able to explain why you get that output. Okay. And also, like if you look at it, this is like safe addition. So I just asked you why you cannot add left plus right and check whether it exceeds the max value. Why you have to check like this? What's the answer? That's what I'm asking. Why you cannot add left plus right is greater than max and check whether there's an overflow? Why you have to say left is greater than max minus right to check for the overflow?
Because it can overflow.
Yeah, so if you add 2 bytes, right, and if the sum of 2 bytes exceeds the max, remember I showed some examples. So if you add 120 and 10, you know the maximum value, the positive value for a byte is 127, right? So if you add 120 and 30, it becomes 130, but when it is a byte, it will turn out to be a negative number, right? Anything more than 127 is an overflow. So it may become like 120 plus 130 may become something say negative 3. So negative 3 is not greater than max, which is 127. So if we do like this, we will not be able to test the overflow. On the other hand, if you test like this, left greater than the same thing, but max minus right, so left is 120, max is 127 minus 3, minus 10, right? Right is 10. So this becomes what, 170. So 120 is greater than 117, so you could now throw an exception. Right? The same thing, instead of checking like this, you check left greater than max minus right. Okay? So same thing with the other thing also. If you want to test for the minimum value, right? Because if you want to add two negative numbers, if you want to add negative 120 and negative 10, it becomes negative 130. But the minimum value of a byte is negative 128, so you cannot go below that. So if you go below that, you will overflow and get some positive value. So negative, if you check for something like this, ideally you will be thinking, okay, negative 130 is less than negative 128, so I should write an exception. But when you do add like this, it becomes something like positive because of the overflow. So if you get something, say 3 plus 3, then that won't be less than negative 128, right? So you won't be able to catch the exception. Okay? So that's why you want to check, for this case, left less than right, max, sorry, min minus right. You just send the right to the other side and check.
So you won't be able to check for the exception if you do it the other way. That's basically the bottom line.
Right. If you do this way, you won't be able to check the exception, but you have to explain that because of the overflow that will happen, so the condition will not be true. So you're checking whether the condition becomes true, right? So because of this, like as I explained, you can even explain some numbers like this. So if you get something less than negative 128 as a result of this addition, it will overflow and become positive. So you cannot check whether the positive is less than the minimum. Alright, so this condition won't be true, but it is really an overflow here. So you don't want to kind of miss that error message. So that's why we will check like this. Okay. So like the safe add code I have given, you should be able to write a safe subtract code. So just one such question. Okay, so since I already given the question, so try to write similar code for subtraction, which is there in the slides. Okay, so let's just change the max, like kind of how you check the overflow here. So
Number 4, Dr. Meg.
okay, so thing is there in the slides too, but let me go over this. So if you're trying to say input 3 bytes A, B, C, you're doing an addition, and I have actually showed some sample inputs. Let's say I pass 34 for A, 123 for B, 45 for C. Let me increase the size. So I pass 34, 123 and 45. And I add all of, not add all of them, 34 plus 123 minus 45. Okay? If you run the code as it is, you will get 112. Why? Because the math, 134 plus 123 is what, 157? 157 minus 45 is 112. But you know, so since 112, if you kind of what you call typecast to a byte, which is the acceptable rate for a byte, because it is like what, less than 127, so you think it's fine. But you know, when you add A plus B, 34 and 123, you get 157. You should not exceed 127, right? So why your compiler, or when you run this program, it didn't generate any exception, or it didn't throw any error message?
Did 123 minus 45 first?
No. you can look at operator precedence,
Yeah.
right?
Yeah.
Both are having same precedence, plus
Yeah.
and minus. So the way program compilers evaluate is left to right. So A plus B is computed first, and whatever it is, minus C. The reason is, internally the addition is done assuming or by upgrading all these variables as integers. Okay, so when your compiler is doing this operation, it will kind of upgrade everything as integer. So A plus B is added as an integer. Okay, so 34 plus 123 is 157. So 157 is a valid integer because it has its own larger range. So then you do a subtraction. And then if the whole thing exceeds 127, then there will be an overflow. But the whole thing is still within the acceptable range. So that's why it did not comply. Okay, so that's the end of answer for this. We went all these things when we discussed that chapter or module. Okay, so this I have given the vulnerable code, and if you see the slides, there is a solution for it. So basically you want to check if x is taking a value of 0, right, then 1 over 0 is what? Infinity, right? So when you try to find the sign infinity, you should basically get not a value or not a number, right? So, but if you do this test, you will get what? If you check if result, you may think result is not a number, and if you try to validate not a number is equal to double dot not a number, you may think it will be true. But whenever you do a comparison with not a number, you have to be very careful. There are only two comparison operators, and equal to is not one among them. And any other comparison operator you execute is not a number, it will always return false. So you cannot check not a number is equal to double dot not a number, because even though you may think that this is like one sign can take real number value, you may think it's double dot not a number and this should be equal to this. No. So if return false, then it goes to else point and prints this result. Alright? So what you should always, how do you fix that? Before you, or instead of comparing like this, you should check using what? Double dot is not a number of result. Have you gone through the code, the slides? I think this is something like this what you have to test. Yeah. Instead of doing like that, comparing with equals operator, you have to check double dot is not a number, NaN of result. That will return true if result is not a number. So if that is returning true, then you will print this error message and you will exit the program. Okay?
I just want to be sure, so how do you have it on there? That wouldn't accomplish anything?
Huh?
How you have it on the document, that wouldn't accomplish anything?
If you, as it is, it will accomplish what? If you pass x as 0, it will print the result is not a number. It's not a number, which means like it's not really what you want. You want this to be printed, right? Because it's not a number. So to print the wrong output. So you want to fix that code, or you fix that code instead of checking like this, you will check like this.
It's not a number, it's the one you want.
I want is the result is not a number, right? Because if x is 0,
Yeah.
1 over 0 is infinity. Sign of infinity is not a number.
Yeah.
So I want is result is not a number if I pass x as 0. That's what I have here.
Okay.
But what this program will print is the result is not a number. It will print else part.
Not a number, which means it's a number.
You can think like that, but it doesn't make sense, right? So you don't want that to be really printed.
Yeah, because the two negatives cancel out. Not a number.
Not in this
like
case.
it becomes a number.
Right, but what you really have is this. So when you really want to print it is not a number.
Yeah.
But if you get that output, it doesn't make sense.
Basically, when you set the result equal, double equal, double, but now
Yeah,
I
do
put that.
this. Okay? How many of you are here? 1, 2, 3, 4, 5. Okay, still some people are missing. So,
And they gonna
you
hate
take
themselves.
advantage of this and don't tell them if you want to.
And they gonna hate themselves Wednesday.
Well, I didn't tell anyone not to miss the class today. So what is the problem with using floating point values as loop counters? There's an example in the slides, right? If you increment 0.1 by 0.1, right? 0.1 may be stored like 0.1000009 or something. So if you want to run it 20 times and check whether if you keep adding by 0.1, it may become 0.2009, and all the way when it comes to 1.9 something, right? It may exceed 2.0, so it may not run 20 times, it may run only 19 times. So that's why it's not advisable to run, use floating point values as loop counters. Okay? And this we went over in terms of what? You want to tell the solution on everything, then there's no fun in it, right? How would you check? This is to do with the two's complement.
The most which one?
Two's complement. You should have read of it, right?
Yes.
Yeah. So, yeah, I think we need to all right, so let's do, for example, if I have, like, if you work with a byte, right, it's 8 bits, I mean byte as a data type. Okay, so by a byte as a data type, we have acceptable values ranging from -128 to 127, right? So the most significant bit is the sign bit, right? So as long as it is 0, no problem. So which means it's positive integer or positive bytes. So you can go from what?
Negative 127.
You can go from all zeros to 0, 1, 1.
1. Okay, yeah.
So that is 0 to 127. Now, what happens if you add, say, if you keep adding 1, right? You keep adding 1, you can get from 0, then 1, 2, 3 up to 127. If you add another 1 to 127, what do you get?
Overflow.
It's an overflow, so you get something like this. So this is 128 as an integer, but as a byte, right? So that's what I'm doing here. I'm passing an integer, all these values for x or integers, and I'm typecasting to a byte. And I'm trying to print what is the value after I typecast it. So if I pass 128 as an integer, I want to see what it gets printed as a byte. Alright? So what it should be printed as a byte.
It Negative 127.
Negative 127.
Negative 128.
Negative 128.
Negative 127.
0 minus 128.
Okay, the way it is computed is the sign bit, right? Once you have a 1 for a sign bit, it basically means it's a negative number. So the rest of the bits, the rest of this 7 bits, right? You find just the integer value of it. So if you add up all these things, it is what? 0, right?
Mm-hmm.
So it is 0 minus the value of this most significant bit is what? The next value is 128. So that's why it is printed as negative 128.
So it's gonna be printed as 128 even if you.
Negative 128.
But you just took 1 from it, right?
Huh?
Then you just the sign bit. If you subtract that 1, would it be negative 127?
No.
Okay.
If you compute like this, if you look at the integer, without the most significant bit or sign bit, what is
Okay.
the value? Minus this bit is set, so that's negative 128. So if all of this is 1, right? So if all of this is 1, it is what? all of the 7 bits or ones, it is
127.
127. So in that case, it will be 127 minus 127.
Okay, I get you.
So that's negative 1. So the range is what? The range is, if you start from 0, 0, 1, 2, all the way to 127. We did this. I remember writing like this on the board. Then it goes to 128, then 127 goes all the way to negative 1. So this is the range. Right? And then ramps back to 0. Okay, so 0, 1, 2 up to 128. So now you can analyze what should be the value that will be printed if you pass your X as 140. Can you try it?
Yes, it could be.
Just try 140 or I'll change the exam, right? Since I'm doing now, I'll change some other integer. I want to be 140. So what is 140 in binary? So let's do that here. 140 in binary will of course have 128 set up, right?
Yeah.
And then this is 0,
Zero,
this
zero,
is 0,
zero.
this is 0, 2, and then this is 136. Right?
Right.
Is that 140? Yes. So then what you should do, subtract the sign bit and basically look at the rest. The rest is what? 4
12.
plus 8 is 12.
Right.
So the value that will be printed is
128,
12 minus
128.
128 is going to be 116.
Oh, okay. Alright. Mm.
Okay, so you run it and verify. You can run this code in your computer and verify what you get. You
Okay.
can practice. You can try, pick up some integer and pass that input to the code, because this code will work, right? So you can test this code. So type this code, pass some integer, and you work it out by hand by yourself and see if you get the same output.
Okay.
So check for 158 what you should get and so on. And of course, it should wrap around. You cannot go more than 256. So if you go more than 256, it will wrap around. Okay, so 255. Okay.
And you said number 2 was in the slides, right?
Right. So the others are more straightforward from the network security chapter. Malware, you have gone through all these things.
Please do that. Please do that one. Please do that compilation one more time. You got me begging on tape, Dr. Man.
Huh?
You got me begging on tape.
Begging?
On tape.
I didn't get it.
Oh,
I'm begging on tape.
Oh, that's fine. Okay, so you have a computer virus that infects, it's a polymorphic virus, we have to remember what all those things mean. It infects some data missing. Okay, suppose there is a virus which is both polymorphic. Okay, so there is a virus that infects computers, right? And it infects, the probability that any given computer is infected within a network is 1%. That's given to you. Okay? And you have an antivirus scanner that can detect the presence of this virus. Okay? And it is 95% accurate in detecting. That means if you have say 100 computers that are infected with this virus, it can identify 95 of them to be infected. Okay? On the other hand, it also means that there could be some false positives. There may be some computers which are not infected and it could identify them as being infected. Alright, so which means if we have say again 100 computers that are not infected and you run this, it may identify 5 of them to be really infected when none of them are really infected. Okay? So, you understand up to this point? That's the problem kind of setup. Now you are running this antivirus scanner on a particular computer that you're interested at, and it prices a flag telling that computer is infected. So now we want to find out what is the probability that the computer is really infected. Okay? So again, let me put everything together. So we have a virus that has 1% chance of infecting any computer that is out there. Okay? And this antivirus scanner that if run can detect the presence of the virus, has 95% accuracy detection. Okay? So it means it has 5% inaccuracy in the sense that it may detect wrongly that something is infected. Okay? So given all these things, you run that antivirus scanner on a particular computer and it raises a flag telling that the computer is infected. So you want to find out what is the probability that the computer is really infected. Okay? So to do this, what you should do, start with some total number of computers that are out there in your network. Okay? So let's start with, you could start with 1,000 or any 100 or anything, you may get some fractional numbers. So if you want to avoid fractional numbers, you could do iteratively and come up with some starting value for the total number of computers. So this is a problem directly I took from the slides. So this starting number of computers this is 4,000. But if you remember what I gave for the quiz, I did give the starting number, so that made your life easy, right? So I could give you like that, but different set of numbers, 1,000 or 2,000 or things like that. Okay? So the virus can infect 1% of them basically. So which means among these 4,000 computers, 1% of them could be infected. So there are 40 computers that are really infected out there. Okay? And you run this antivirus scanner on all the 4,000 of them, and you know by now that 3960 are not infected, right? And only 40 are infected, right? So it has 95% accuracy, means if you run on 40 of them, it is going to say how many of this 40 are really infected. It has 95% accuracy.